So let's talk now about system calls. System calls are the interface between an application and the kernel. Okay, remember again that the kernel is running in kernel mode, while applications run in user mode, right? So user mode has some limitations on particular instructions that can't be executed, while the kernel mode has access to all instructions. So the system calls, there are a lot of different services that a kernel can provide for system calls. So some examples are processes. So this would be, think of processes right now as another word for application or program. Okay, we will look in a lot more detail at what processes are later. So processes, starting, stopping processes, things like that. Memory allocation is a big thing that kernels usually provide. And what else do we have? We have, for instance, file system. So we might have within a file system, system calls that operate, let's say, on directories. Or file names, for instance, renaming example would be an example. We deal with, let's say, the contents of a file. So the content of a file, we might talk about something like reading or writing from the file. We might deal with various file attributes. For instance, maybe setting a permission, something like that. What else do we have? Well, we have security, networking, certainly a big set of system calls, dealing with those. And we really have lots of others as well, depending on the operating system. So let's look at a little more detail of how system call actually works. Okay, so we have our application. Let's look, for instance, at an application, and it might be make two system calls. So actually, let's just look at a single system call right now. So we might call write with file descriptor, which is an integer, a pointer to something to write, and the number of bytes to write. So our application is trying to write hello to either some file or to the standard output or something like that. Okay. We talked about the fact that a system call is made from the user mode to the kernel mode by issuing a specific instruction. Okay. In our case, what we're looking at for the x86 is we're going to be looking at a trap instruction. So we issue a trap instruction, and that's going to cause the processor to do two things. It's going to switch from user mode to kernel mode, and it's going to go into the kernel at some specified location. Okay, not randomly into there, but into some specified location. Let's say in this kernel it's set up so it goes to a trap dispatcher. Right? The trap dispatcher looks and says, okay, what kind of a system call is this? And then dispatches it appropriately. So in this case, if we're doing a write, it's going to go to the write implementation in the kernel. And when that's complete, it's going to come back to the trap dispatcher, which will then return back to the instruction that caused us to go into the kernel, which was the trap instruction. So that'd be all well and good if the write code here actually generated a trap instruction. But the fact is it doesn't. If you look at the compiler, as the compiler's compiling this, it looks along and it says write. Oh, write's just a function, like any other function, foo or main or whatever else. It's a function. And so therefore, it's going to call a function, okay? But it can't call into the function of the kernel because we are limited by our memory map to not allow us to get into the kernel directly. It would be bad news if processes could just randomly jump into various places in the kernel. So we have this very constrained interface, which is this trap interface. So we've somehow got to generate a trap instruction, but I'm saying we can't do that from C. So how do we do it? If we can't do it from C, we'll do it in assembly language. So what we'll have here is a system call library. And the system call library will have entry points or implementations for every system call. Among others, it'll have an implementation for write. So write is going to get called from C. So as far as the C program is concerned, it's just another C function, but it's actually implemented in assembler. Okay, and it's going to have these parameters on the stack, the file descriptor, the hello, and 5, and it's going to, as well as the return address. So it's going to go ahead and do a couple things, and then it's going to push onto the stack. So it'll push on the 5, it'll push on the hello, it'll end up by pushing the file descriptor, and then it's going to push a number that specifies which system call this is. So this could be, let's say, a constant, let's say write num. Okay, and every system call would then have its own unique integer value for this. So the trap dispatcher, so the write call pushes the 5, pushes the hello, pushes the file descriptor, pushes write num, and then goes into a trap. The trap sends us into the kernel in kernel mode in trap dispatch. Trap dispatch can look at the parameters on the stack. Notice that there's write num. Say, oh, write num, that must mean it's a write call. I'm going to go ahead and set the parameters appropriately so they can go to the write implementation in the kernel. Go in there, write does its thing with full privileges, right, because we're running in kernel mode, and then returns to the trap dispatcher, returns back to the trap instruction. This will return back to the end of the write. So that is how we actually implement system calls.